So this is 9.3 continued. Let's start this problem a little bit, at least, over again. We're supposed to carry out a test to investigate the researcher's question about the depression. If caffeine deprivation has no effect on depression, then we would expect the actual mean difference in the depression to be 0. We subtract the before and after. The placebo minus the caffeine should be 0. So we have the null hypothesis. The mean difference, mu sub d, would be 0. The alternative greater than 0, if you took the I guess it's the caffeine minus the placebo, should be more positive values, and that's why we did it in that order, to make sure that this would be greater than 0 instead of less than 0. Placebo minus caffeine, depression scores. I guess the placebo would have higher depression because the caffeine would help, I guess. We chose this order of subtraction to get more positive values. That's why we went with the greater than 0. No significance level is given, and so alpha being 0.05, the 95% confidence, that's used an awful lot. If conditions are met, we should do a paired t-test for mu sub d. Researchers randomly assign treatments, so it should be random. 10% condition, we aren't sampling, so it isn't necessary to check the 10% condition. It's interesting that condition is not necessarily this time. The normal and large sample size, we've only got 11, so that doesn't take care of our normal distribution, and we don't know that it's normal beforehand. So we better look at some things like a histogram, and you might say, oh, that doesn't look very bell-shaped. Well, it's not horrible. It's at least not backwards, so it's sort of bell-shaped. This box and whisker, there is sort of the box with the line, the median right down the center. This whisker could be longer, or this could be moved to the right a little bit more, but no outliers. Not quite straight, but about half and half. So it's not horrible. Histogram is irregular, so few values. Box plot shows some right skewness, but no outliers. Normal probability plot, slightly curved, slight skewness. No outliers or strong skewness. T procedure should be okay. Enter the differences in list L1. So you could, if you wanted to, put the before the placebo, I guess, and the caffeine in L1 and L2, and then L3 would be your differences. You could do L1 minus L2. But we'll use the calculator's t-test and the draw command. We get a test statistic of 3.5304. The p-value, this is not for a proportion, this is the area under the curve, 0.0027. You can't even see it when you draw it here. It's supposed to be that greater than, at 3.5. 1, 2, 3.5 is right here. You can't see even any problems. That's why this p-value is so small, 0.0027. Area to the right of t equals that. 11 minus 1, or 10, is the degrees of freedom. Because the p-value is really small, and it's smaller than 0.05, which is what we're used, the alpha, then we reject mu sub d equals 0. In other words, we reject that there is no difference. We have convincing evidence the true mean difference, placebo minus caffeine, in depression scores is positive for subjects like these. Carrying out the significance test is pretty simple, especially if you use a calculator or a computer. Tests wisely. It's not so simple. Some points to keep in mind when using or interpreting significance tests. Smaller significance level requires stronger evidence to reject the null hypothesis. So, the smaller the alpha. 0.05 is not bad. 0.01 can be better. You need then stronger evidence to reject the null. And it all depends upon what you choose the null hypothesis to be. Higher power gives a better chance of detecting a difference when it really exists. And that's the beta. And that's harder to determine. But more, a larger n, a larger sample can be helpful, certainly. And the smaller alpha makes a larger beta, but that makes the power smaller. So all these stuff are connected. Any significance level and desired power, detecting a small difference between the null and alternative, requires a larger sample. So the bigger the sample, the better. But you can go crazy too. Practical importance. When the null hypothesis, no effect or no difference, can be rejected, at the usual levels, there's good evidence of a difference. Don't go crazy by making these so small that you reject things or so big that you reject them. These are the normal 0.05 and 0.01 levels. The difference may be very small, though. And when large samples are available, even tiny deviations from the null will be significant. So now large samples can be a problem. So how do you use these wisely? Multiple analysis. Statistical significance ought to mean that you have found the difference you were looking for. The reasoning behind statistical significance works well if you decide what the difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. So this is doing the whole process with that decision made beforehand. Significance may have little meaning if you're not careful. So that's tests about a population mean. We'll have to go through some examples for the review for the Chapter 9. Thank you, and good night.